Hello, this is Chris DeSalvatore, and in this tutorial, we're going to be creating a finite element model, and then we'll generate a single quad element from that. Then we'll use the AutoCAD array command to create a grid of elements, which we will then extrude and revolve into 3D solid elements. Then we'll input radiation to the elements, applying temperature boundary conditions and solving the problem running SINDA. So let's get started. We're going to start by going into thermal, thermophysical properties, and edit property data. Now we're going to add aluminum as a property. So we click in the new property to add window at the top. Type in aluminum and go ahead and click add. And we're going to put in 240 for the conductivity, 240 watts per meter per K. And we're going to be doing a steady state run. So we're not going to need specific heat and density, but we would need those if we're running a transient. So we're just going to leave those at the default values. And we hit OK here, and aluminum, as you can see, is entered with the conductivity value updated. So we're going to generate our nodes now. So we'll go into thermal. FEM network and node. And we're going to create 4 nodes. We're going to start at the origin. So the first node will be at 0, 0. So it's 0, comma 0 for X and Y. And then since we just entered the node command, we can just hit enter again and we'll be back in the node command. So it's a 1, comma 0 to put the second node up 1 unit on the X direction. And enter again. We're back in the node command, and the third node will be at 1, comma 1, and enter again. And our fourth node will be at 0, comma 1. And we can go ahead and hit view, zoom, extents. And there are our 4 nodes created. And now that we have our 4 nodes, we can create our element. So I'll go ahead and go back into thermal, FEM network, and go to element this time. And it's going to be important to select the elements in a particular order. So that can be either, in this case, clockwise or counterclockwise. I'll go ahead and do this clockwise. So I'll hit first node, second, third, fourth, hit enter. Now we have our element generated. If I had chosen this node down here and picked over here and there, it would not have generated the element in the way that we were intending. So now that we've done that, we can go and select the element. And go into thermal edit. And we're going to give it a conductivity. So we're going to go to the conduction tab at the top. And we've defined it for the aluminum material. So we need to go down here to material, hit the drop-down menu, and hit aluminum. We got a thickness of millimeter there. That's not really going to be that important in this demonstration. So we can just leave the default and go ahead and hit OK. So now that is defined as aluminum. So now we want to create an array of this element. So we'll go into modify array, rectangular array, and go ahead and select the object that we're going to create the array from and hit enter. Now, depending on your version of Thermal Desktop, this is 24.2 Service Pack 2. The current version as of December 2024. A array is generated automatically in this case. But as you can see down in the command line, we have a number of options that we can pick. So I can go ahead and pick the rows. And it shows that 3 rows are defaulted here, but we can change that here. We're going to want 4 rows actually. So I'll hit the 4 in the command line, hit enter. It added an additional row. Now, after we do that, we're going to have the option of specifying the distance is, in this case, 1.5 is the default, but we're going to want 1 because these are 1-inch squares. So I can type 1 in here, and I can close up the elements by doing that. And this option that opens up next is to give you the opportunity to do elevation, but we're going to do this on the XY plane, so we don't need that. So I'll just go ahead and hit the 0 default. And it brings us back to the original array command. And we want to control the columns now. So I'll go ahead and hit columns. And you can see that the 4 columns is defaulted, but we're only going to want 3. So I'll type 3 in there. Hit enter again. You want to close that up and hit 1. And you can either type in the command line or type in the field by the cursor. Either way is going to work in this version of Thermal Desktop. So I'll go ahead and enter that. And we are complete with this command. So we can go ahead and exit out of that. Okay, so the next thing we're going to want to do is go into Thermal, Model Checks, and Show Free Edges. And we're going to select the entire model here. So there's a couple ways we can do that. I can either take and just sweep a field with the cursor over the whole model, or I could have typed all in the command line. That would have done the same thing. And I can go ahead and hit enter. Okay, so now we have 48 free edges found. So what's happened here is that the array command has copied the nodes as well as the elements, and the nodes are lying on top of each other. If we output the model at this point, there would be no conduction between the elements, so we have to resolve that. And we do that by going ahead into Thermal, FDFEM network, and merge coincident nodes, which is over here. And again, I can sweep over and type all in the command line. I'll do all in the command line this time. Okay, so at this point, I'll hit enter. And the coincidence tolerance field comes up. And in the case of this model, we'll want to type 0.01. That should be sufficient for this geometry. And we go ahead and hit OK. And it's asking us, is this what we really want to do? And yes, that is what we really want to do. And now we regenerate the model. Just type regen into the command line. You can either select it from the drop up menu here, or you can just enter at this point, either way. So now the model's been regenerated. Okay, so now at this point, we want to go into Thermal and go into Model Checks and Show Free Edges. And we're going to select the entire model and hit enter. Okay. Okay, so all the free edges have been filtered out at this point. So now we go into Thermal, FDFEM network, and extrude planar elements into solids. Okay, so what we're going to do here is build the top part of our feature. Okay, so it is asking to select the point to extrude from, and we're going to extrude from the origin. That'll be 0, 0. And now it's asking us to select the point to define the extrude vector. And we're going to make this 5 inches in the z direction. So that will be 0, 0, 5. So now the planar elements into solids dialog box comes up. And okay, we're going to want to leave the even breakdown selected, the dot in the circle over here. And we're going to, the 5 inches is already in there, but it wants to know how many solids we want to create along the path, and that's going to be 5. So we'll type in 5 there. And then select OK. So now you can see we've got our the top of our feature created. That's 5 inches above the original XY plane. Okay, so what we want to do here is go ahead and go into viewpoint. It should be viewpoint. I'm going to type into the command line. Okay, so what we're looking at is the whole model, and we've got every feature through the exterior and interior of the model shown here. But if we go ahead over here, we can see that the from viewpoint, the viewpoint that we're looking from down here on the x-axis is 225 degrees, which is the southwest angle that we're looking at the model. And the XY plane, we've got 35.3. But if we change that to 30 degrees, and okay that, you can see that we've got a lot of clutter if we're going to look at different angles of the model. And like I said, that's just the interior of the model. And we're going to want to hide the visibility of that because when we go and we run a case, the way that Thermal Desktop runs, if we get too many graphic features, it could really bog down the program, especially if you have a really large model. So at this point, we're going to want to go into Thermal, FEM network, and hide solid interior faces. It's all the way at the bottom. Okay, so that click right there caused them to disappear. So now the program will solve a little more efficiently by doing that. Like I said, particularly with large models, that's helpful to do that at that point. Okay, so now we want to go into Thermal, FEM network, and revolve planar elements into solids. Okay, we're going to create the bottom part of this feature in this series of commands. And we're going to want to select the model and go ahead and enter at this point. Now it's asking for the base point to revolve, which is going to be at -3, 0. Basically, what we're going to do is we're going to create the axis to generate the bottom part of the feature, which is going to be a quarter circle. And now it's asking to select the point to define the revolve axis. That's going to be -3, 3. Okay, so now we're in the extrude revolve planar elements into solids dialog box. We're going to want to leave even breakdown selected. And the total distance in degrees is going to be 90 because we're going to want to make a quarter circle. And we're going to want to select in solids created along the path. We're going to want to make 9 there, so we'll enter 9 in that field. And we'll select OK. And you can see that it's generated the bottom part of our feature here. Okay, so next we're going to want to go into thermal, FD-FEM network, and surface coat free solid FEM faces. Okay, so what we're doing here, we'll go ahead, it's asking us to select everything. I'll select all. Okay, this defines the faces of the feature as aluminum so that the radiation command will execute properly, so it knows it's an aluminum surface. Okay, so now that we've selected that, we go ahead and hit enter, and we get the shell data multiple surface element edit mode dialog box. And we want to hit the conductance capacitance tab and tell the program that this is aluminum material for this function. And we'll hit OK. And it's saying that we made that change. And do you want to apply the changes? We go ahead and select that. Okay, so now we're going to want to define our boundaries, which will be the top and bottom of the feature. So in order to facilitate selecting that, we'll go into View, 3D Views, Front View. Okay, so this will enable us to make the selections to define our boundaries. So I'm going to select the top. I'm going to go ahead and we're going to go into thermal edit. And we're going to select the nodes here. Now we can either hit OK or double click on nodes to bring up the field that we want. And here we're going to want to select override calculations by element surfaces and then hit boundary. And we're going to define temperature at this boundary as 373.15 degrees Kelvin and hit OK. And this window is enabling us to apply the changes. So we go ahead and hit that. So we got our top boundary defined now. And now we want to define our bottom boundary. So we'll select down here and go back into thermal edit. And we go to nodes again. And we do the same thing. We want to override the calculations by element surfaces. We want this to be a boundary. And on this end, we're going to define it a little bit lower at 273.15 degrees. So we got a good separation of boundaries to give us a gradient in the results. So we'll go ahead and hit OK there. And same thing, apply the changes. So now we got our boundaries defined. So what we'll want to do at this point is to go into thermal modeling tools and resequencing so that the IDs defined in the feature will be shown in order. And certainly that'll make deciphering the results a little easier to do. So I'm going to select everything. Okay. And we'll go ahead and hit enter. And for the purposes of resequencing, we're going to start at 1 since this is the that's the only feature that we have in this analysis. So we'll just start at 1 for that. If we had multiple features, we may want to start at a different number. And we're going to want to increment at 1 so we can leave the defaults there. So we'll hit OK. So now we're ready to run the case. We can go either into Thermal Case Set Manager and edit, or we can go directly to the case sets here. And that brings up our case set manager. And we can see that the case has been established here. And we want to go into edit. And we can see we're defaulted to steady state here. And again, if we were doing a transient run, we would need the specific heat and density defined, but we're not doing that. So we're just looking at the conductivity. So steady state is selected. So we're all set there. And we can go ahead and run the case. And now the program is crunching and generating our results. And it completed successfully. And with this window here, if you wanted to look at the text of the run and the log, you can click either one of these buttons here. If it did not run successfully, those are useful to look at to identify the problem and then resolve it. So that's very useful for that purpose. So we got our results. As you can see from our color-coded bar on the left side, the top where the boundary is at 373 degrees. It's near to that, and down at the bottom, we got 273 degrees, and it's near to that, and we have our gradients along the way, which is showing us the resultant temperatures down through the feature. So that is the way to run for radiation and conduction using finite elements. Hope you enjoyed that and got something out of it.